Hello, welcome to video 175 on Financial Math for Actuarial Exam 2. I'd like to start this video off by being a bit more personal than I usually am, then we'll get on to the math. Those who follow me closely know that for about the last week and a half, I haven't posted any videos on YouTube, and I haven't written any articles on my blog, infinityisreallybig.com. There's been a good reason for that. It's been a hectic but exciting time in the Kinney household. My oldest daughter just got married this last weekend. It was a very beautiful ceremony, a chance to be with other people and reflect on life. And it brings out the fact that you may think math is the most important thing to me. I make so many videos and I love math so much, but it's not. It's not the most important thing to me. The most important thing to me is my faith in and love for God and who He is and what He's done. And then my faith and love for my family, my wife and my kids, my extended family. Those are certainly the most important thing. More important than math, more important than my job. I hope those kinds of things are more important to you, more important than whatever you do in your job. Not that job and math are unimportant, those are important things, but there are more important things in life. And to me, being thankful to God for those things, both my family and math and my job, is part of what makes God number one. Alright, let's go on back to the math content for this video. So you see here that we're doing a modified version of exercise 7.2.2 from the 7th edition of Berman. As I've been doing recently, when we've been talking about the subject of immunization of liability cash flows by asset cash flows, I'm kind of tying this with recent videos. This is most related to videos 173 and 174 that come right before. It's going to be another tough video. You're not going to really understand what's going on here unless you watch those two videos first, okay? So make sure you do that. If you have watched those first, now we can get on to the problem, and you see it's a very long problem statement. Here's where I start the exercise itself, 7.2.2. It refers back to an example in the book, however, example 7.5, and so I've got a description of the start of that example right here before we get on to the actual exercise itself right here, and my modification down here. Okay, you can see we're doing work in a spreadsheet here, although I do have Mathematica in the background, and we're going to look at some equations that I've talked about recently in the Mathematica document. All right, let's read it here. So we have a small company that is terminating its operations, and as you read further, it's not in the immediate future, it's evidently after the 3 employees retire. It's decided to provide each of those 3 employees with a severance package, some money. First of all, it pays $10,000 per year at the end of each year, up to and including age 65 when they retire, plus a lump sum payment of $100,000 at age 65. In case one of the employees or more than one dies before age 65, we assume, for the sake of simplicity, that these payments still continue to the beneficiary until the employee would have been age 65. And also, for simplicity, we assume the 3 employees are right at their birthdays right now at exact ages 50, 53, and 55. Okay, so the first one has 15 more years, the second one has 12 more years, and the third one has 10 more years. All right, now we're on to the exercise statement. Based on that background, the company decides that they want to cover those liabilities, the severance package payments, with some asset income. A level annual payment annuity immediate. That's going to make payments at the end of every year. It's got end payments, where end could be different thing, which is not necessarily related to the amount of time they have before they retire. The interest rate, I, is taken to be 10%. Again, constant for simplicity, we're assuming a flat yield curve. For each of these 4 values of n that you see, 5, 15, 50, and 100, it seems funny to do the 100 one because that would be going long into the future. We want to find the annual required payment to match the assets with the liabilities and calculate the sum of these 2 kinds of quantities, where the ATs represent the asset payments and T is the times and V to the T is the present value discount factor raised to those times. Couple things to do here. First of all, which value of n of these 4 that you see here, 5, 15, 50, and 100, provides the nearest match of the sum of the products T times LT times V to the T, where LT represents the liability payment at time T. Okay, so the durations are almost matched. That's the goal there. It's not going to be an exact match of durations, but you're hoping that they're almost matched. Which one is closest? But then the directions also say to solve for the quote-unquote exact value of n. I added the quotes, by the way, where these sums are matched. Is there some other value of n that's not one of these four, where these sums are even more closely matched? Determine whether this provides Redington immunization for the portfolio. And my modification is to also solve this problem with a spreadsheet rather than just pure algebra. And I also want to compare something else, some sums that we talked about in the last video, okay, or two. Before we get into actually solving this with the spreadsheet, I should mention something else. And that's that the answers, both in the back of the book and in the solutions manual, are, well, if not wrong, they're a little bit misleading. So here's Broberman's book, 7th edition. If you go to the back and look at the answer for 7.2.2, it's down here. Hard to do this backwards here when I'm trying to look in both places. And what's written there is not wrong, but it's the only thing that's written for 7.2.2, and what that means is it doesn't address this question, or this thing to do, solve for the exact value then at which these sums are matched. And it's also misleading as far as the last part of the question, determining whether this provides Redington immunization for the portfolio. Is that referring to the n that's either 5, 15, 50, or 100, or this other value of n at which these sums are more exactly matched? So that's not clear. So that's one defect. If you look at the solutions manual, that looks like this. Here's the solution for this in the solutions manual. It's a bit more comprehensive, but still a little bit misleading. It's got that exact match, quote unquote, occurs at n equals 20, which is a different value of n. However, it says, but there is no immunization in that case. But that's actually wrong. There actually is immunization in the case where n equals 20, as we will see as we solve the problem. So there's no immunization in the case where n is 15, which is the solution to the first part, but there actually is immunization when n is 20. So both the back of the book and the solutions manual that are printed are not ideal, okay? So I will try to rectify both of those things as we go through this. All right, so I have the spreadsheet here somewhat set up for us. I'm going to make this a bit bigger. I'll cover myself here a little bit more so we can see more. I've got I0, the interest rate that we're dealing with. I'm going to figure out V, the present value discount factor. I've got employee 1, the one who's 50 years old, has these payments not starting at time 0. This is different than what we've done recently. Starting at time 1 year from when they are 50, when they turn 51. 10,000, then 10,000, etc. Then when they turn 65 in 15 years, there's the 10,000 plus another 100,000, 110,000. Employee 2 is the one who's 53 years old currently, and that's the liability cash flows for employee 2. And then employee 3 is the one who's 55 years old. This is the liability cash flows for the severance package for employee 3. Okay? I want to fill in the spreadsheet. You can see the values that I'm filling in, and I'm going to do some summations like is asked for. I'm going to find some present values in Macaulay durations and some other kinds of sums. Okay, you can get a little feel for what I'm about to do here. Fill in the spreadsheets to try to solve the problem. Before I do that, let's look at some equations to review those. Let's first review Macaulay duration. That'll be good to review here as we think about this. And this is also going to tie into the next video, video 176. Okay, this is a little preview of what's going to come in video 176, when I'm going to essentially review what we do here and then add something to it. So Macaulay duration, suppose a term structure is flat with effective annual interest rate I and cash flows K1 through Kn, which could also be written as A1 through AN or L1 through LN, depending on whether they are assets or liabilities, occur at times T1 through Tn. The Macaulay duration is by definition this fraction here. Okay, this is something that you can find in Broberman's book. It's something that I talked about in videos, 10 to 20 videos ago. I did a lot of duration problems, both Macaulay and modified duration problems. Actually, I did change things a little bit here. in this notation here. I'm making these times T1 through Tn be arbitrary. Back when we did duration, they were actually taken to be whole numbers, 0, 1, 2, 3, etc. up through n, say. But here, we're taking them to be arbitrary. I am implicitly assuming, although I guess it's not necessary for the formula, that T1 is less than T2 is less than T3 is, etc., less than Tn. It doesn't really matter for the formula, though. I want to remark that this is something I've remarked before, that we can do a little algebra and index changing of the summations to rewrite this fraction in this way as a weighted average, really, of times of payments, where these weights, WMs, are these quantities. How did I do that? Essentially, this quantity can be thought of as a constant with respect to this summation. You can kind of put it out in front as 1 over this quantity, and then you can bring it inside the summation and change the index of summation to, say, an S or something else, so it's not confusing. These are the weights for this weighted average of times of payments. Thus, that's what I say here. Thus, the Macaulay duration is a weighted average of times of payments, and the weights themselves also add up to 1, as this algebra shows. Okay? That's going to be important for the next video, because I'm going to tie this kind of stuff to probability. Okay, that's going to be the I think, kind of neat thing that's going to come up in the next video. Let's also review Reddington immunization and what we talked about in the last few videos. We've also seen that if we have asset and liability cash flows at these times, then we'd have the present value functions both for the asset and liability cash flows. And we assume that these have been matched at some specific interest rate, I0. We've seen that this condition, that the derivatives of these functions at I0 being equal, is equivalent to these summations being equal. And in the spreadsheet, we're going to be computing these summations that you see here. And furthermore, we also saw that if we assume these derivatives are equal, then with the following 3 things are equivalent and imply we have achieved Reddington immunization. The second derivative of the asset cash flow present value is greater than the second derivative liability cash flow present value at I0. This summation is greater than this summation, and this summation is greater than this summation. Okay? So these are the kinds of things you're going to want to be thinking about, pausing in the video and writing down as we now go back to the spreadsheet so you can follow what I'm doing. Okay? So keep that in mind, have a sheet of paper so you can refer to those things. Now let's go ahead and go to the spreadsheet. Okay, I'm going to go faster through spreadsheet usage than I did before in the last video, assuming you've done spreadsheet usage, that you've watched that video. I got I in cell B19 here, and I want to calculate V as 1 over 1 plus I. I can type that like this, 1 over 1 plus B19 in parentheses like that. I don't need the dollar signs around the B here to fix that cell reference to make it an absolute cell reference. This is going to be good enough. When I do refer to cell B20, which I will need to do a lot, then I will use dollar signs to fix the cell reference to make it an absolute cell reference. So there we saw that in the last video. V is 0.90 repeating. Alright, let's start to fill in what comes next. Again, keeping in mind what the goal is to find these sums that you see here for these different values of n. In my modification, we're using the spreadsheet to help us do that. We're also trying to find these sums and compare them. So we need to find, first of all, the liability cash flows, which are just found by adding up these individual liability cash flows for these 3 different employees. So I could do, here I could do equals B23 plus C23 plus D23. I could also do equals SUM, the sum function, B23 colon D23, like that. Either way is okay. This one's going to be better in general if you had a lot of columns instead of just 3. 30,000. And then we want to go on down to time 15, where we have 110,000 for the final amount there. By the way, the times here do go on to down to time 100. You can see in a row 123, I think it is. Oh, no, 122, excuse me, right there. There's time 100. That's because there was that n equals 100 case that we had to deal with. So that's why it goes way down there. You can ignore these little triangles, it's not a big deal here. Next thing we want to do is we want to find the discounted values of those liability cash flows. We want to multiply by v to the t power. So here I can do equals E23 times v. Now I want to use dollar signs. Absolute cell reference $B, $20 is where v is, and that's going to stay fixed as I copy and paste downward. That's what the dollar signs do. The first dollar sign again fixes column B, the second fixes row 20. The second one's really all that's necessary here, but it's okay. And raise that to the A23 power, the t power, like that. Okay? These are the discounted values. There they are. What is the present value of the liability cash flow at interest rate I0, which is 10%? I would need to add up these present values. Use equals SUM. Equals SUM of these things. 300,000. Okay? It does come out to exactly 300,000. That's what happens in this particular problem. Next thing we want to do, looking at the directions here, is, well, we want to find a match for the sum of these things here. So we are going to need to find these things, these products here, t times LT times v to the t. Let's do that next. So I have equals A23, that's t, times LT, which is an E23, times v to the t, use dollar signs again, B20 to the t power, A23 power. Take a look at that, make sure it's right. Looks good to me. Copy and paste that downward. There we go. And so now we want to find the sum of those things. Use equals SUM again. By the way, you can just click and drag here to highlight those things. There's the sum, and that is a correct answer, one of the answers that you'll find that's correct in the back of the book and the solutions manual. The sum is, let's see, 2,262,077 approximately. What's the Macaulay duration? That's not asked, you're not asked to find that in the problem, except I'm going to need it from my modification. Let's go ahead and find that. If you think about it, based on what I have back here, Macaulay duration is this ratio here. I already have those values. The top of the ratio is this sum, the bottom is this one. So I just do the ratio, this divided by this, F19 divided by F18. Macaulay duration again is a weighted average of times of payments. These payments are times 1 through 15. The answer's got to be somewhere between 1 and 15, about 7.54. All right. What next? Let's go ahead. In the directions here, it doesn't say you have to compute the sum of t squared times LT times v to the t, but that would be helpful if we are going to decide about whether the portfolio is immunized or not. So let's go ahead and do that anyway. So we want t squared equals A23 squared times LT E23 times v to the t, $B, $20 to the A23. Double check that. Enter it. Click and drag. We get these numbers, and then I am going to go ahead and find the sum of those things by again using equals SUM like this. Okay? This is going to help us again decide about immunization. We haven't thought about the asset cash flows yet. We want to ultimately match durations as well, which n gives us the closest to that matching. And for that particular value, and we also then want to think about whether we are immunized or not. I'm going to skip this sum for the moment. We'll come back to that. We'll do that at the end. Let's figure out these values here before we start filling in the columns for the asset cash flows. So n, well, what's going to go here is going to be either, looking at the problem statement, either 5, 15, 50, or 100. Let's go ahead and first just put a 5 in there. Okay, I don't know the asset cash flow yet. I want to figure out what that is. If n is 5, and this is a level annuity immediate, then I'm going to get 5 non-zero numbers here for those 5 payments. If n is 15, then I'll get 15 numbers here. If n is 50, I'll get 50. If n is 100, I'll get 100. And I got to figure out what those payments are. What is the value of AT? And it's going to be a level payment, a constant payment. To figure out AT, by thinking about the fact that this is an annuity immediate, I better figure out little an, right? Your present value of your standard annuity immediate with payments of 1 at the end of every period. I need the formula for an. Think about that for a second. That's 1 minus v to the n divided by I. So in this case, use parentheses here, equals 1 minus v again is in cell B20. Use, I guess I don't need dollar signs here actually because I'm not going to copy and paste B20 to the n power. N is in cell K15. All divided by I0. I0 was in cell B19. Okay? Think about what this should be. This should be something between 0 and 5. 3.79. Okay? Now think about how to figure out these level payments. You would want those level payments, whatever they are, times the present value of your basic annuity immediate to equal the present value of the liabilities, to match the present values. Okay? So think about that. That means we need to really take this number and divide by this number. Equals F18 divided by K16. 30,000 divided by 3.79. In the case where n is 5, the level payments are going to be 79,139. If n is something different, these things will change. If n is 15, they change to that. If n is 50, they change to that. If n is 100, they change to this. Okay? So changing the value of n will update those things. Now we need to be careful for what we put in this cell here. I do not want to just do equals B17 or even $B $17. If I could type correctly. Or, sorry, equals $K $17. I don't want to just do that because, think about it, why not? Because for different values of n, it's a different length of time for the annuity immediate. And after the certain value of n that you have, like n equals 5, the payments are all going to be 0 because the annuity immediate has stopped. So how do I deal with that? Key thing here is to use a conditional, if. And what kind of conditional will it be? You can see the syntax here is it's got a logical test. If that logical test comes out true, you put a comma, and whatever the value is, if it's true, you want to put in the second slot. Then put a comma, and you put the value if it's false. So I want it to be AT if what? If t is less than or equal to n. Else, otherwise, I want it to be 0. So I can do this. If t, which is in cell A23, is less than or equal to n, which is in cell K15, and I better use dollars for that one, then I want what's in cell K17, capital A, $K $17, comma, else, otherwise, I want the output to be 0. Let's see if this works. So this is what's going to happen when n is 5, and notice the first 5 numbers are what you see here for capital A in cell K17. If I change n, make it 15, I get a different value for capital A, and you don't see a bunch of zeros anymore until you go down further, until t gets past 15. Now you see a bunch of zeros. Okay? So this is what you want to do. I hope you got that. Okay? If not, go back and watch it again. I'm going to copy and paste this down all the way to t equals 100. And that will include the case where we think about what happens when n equals 100. Get a bunch of zeros there, but if I change n to be 100, then none of those numbers are going to be 0, including down at t equals 100. There you see it, okay? So that's the way to program that to make it work for any value of n. Now we want to discount these things. So multiply here equals J23 times V to the T. V again is in cell B20. to the t power, which is in A23. Double check that. These are going to be the discounted values, copy and paste it all the way down. Even if I didn't have n equals 100, if I only had it to be 5 or 15 or whatever, I'd want to still copy and paste all the way down. I would get a bunch of zeros in that case. Here again, I'm not. Again, the last row here, the address is K122. I want to add these things up now to get the present value of the annuity cash flow. So equals SUM K23 through K122. Then I want to find, as in the directions say to do, the sum of t times a t times v to the t, so I need to fill in this column next. So I'll try to go fast here. I know this is getting long. A23 times J23, which is really a constant, so I could just refer to that constant, which is also in cell K17. But I'll just go ahead and do J23 times v to the t. Actually, I could just refer to cell K23 here. Maybe I should do it that way. Like that. So that's t times, in parentheses, a to the t times v to the t. Click and drag this. Trying to click and drag a little faster here. What's the sum of those things? Equals SUM K23 through L23 through L122. Notice these sums do not match. Durations are not matched here at when n equals 5. To find the durations, do this divided by this, just like before. Again, it's a weighted average of times of payment. Here the payments occur between times 1 and 100. This is something between 1 and 100. 10.99 is the weighted average of the times of payments. Bigger than this one. It's got a bigger duration. Let's go ahead and calculate this thing here. Again, I can do it this way. Of course, the problem when you go too fast is something like that happens. Sorry about that. I won't bother cutting those out here. Equals SUM M23 through M122. There's that sum. Okay. Now again, I'm leaving these sums for the end. Well, let's try to wrap this up here. Okay. Here, when n is 100, excuse me, the durations are not matched. When n is 5, the durations are not matched. When n is 50, the durations are not matched. And in fact, when n is 15, the durations are not matched. This is not matching that. However, when n is 15, they're closest to matching. Okay? So that's why n equals 15 is the answer to the part of the question that says, for each of these values of n equals 5, 15, 50, or 100, are we most closely matching? Okay? These durations are closest for those 4 possibilities when n is 15. And in that case, I think also the sums here, yes, the sums here and here are most close, although they are still far apart. But then again, the question says, solve for the quote-unquote exact value then for which these sums are matched, evidently some other value then besides these 4. And the solutions manual confirms that. And so by experimenting, you could try different values of n here. 16, see if these are getting closer. They are. 17, etc. You eventually get to n equals 20, and they're relatively close. 226, 2077, and 225, 2422 are, relatively speaking, fairly close. If you go up to n equals 21, they get further away, although you'd have to double check that. I guess you can see it visually here. These are now further away again, and these are further away. N equals 20 is when you are most closely matching durations and these summations that you see here. So that's the answer to that question. Now what about immunization? When n equals 15, the first 4 choices, that's of those 4 choices giving us the most close match of the durations, we are not immunized. The sum of the t squared times lt times v to the t is bigger than the sum of the t squared times at times v to the t. we need for this thing to be bigger than this thing to be immunized. And so that's not happening. So in the n equals 15 case, we're not immunized. But when n equals 20, where we have an even closer match of durations, then this number is bigger than this number, and we are immunized. So that's why the answer in the solutions manual as well is not quite right. Okay, that was a lot to take in. I guess I'm not quite done. I want to figure out these sums. And again, this is worth it for the next video, video 176, because again, I'm going to bring probability into play and means and variances and standard deviations if you know about those things. So let's go ahead and calculate these sums to finish off this video. If you don't care about this, you could skip it, I guess. So we have A23 minus the Macaulay duration, which is in cell F20. By the way, the Macaulay duration is essentially a mean. That's one hint to where we're going. Times LT times V to the T. Let's just see that there's the same relationship with the inequalities here. That's the goal. Copy and paste this down. I guess I don't have to go very far with that one. And then we do the same kind of thing over here. Equals A23 minus Macaulay duration for the asset cash flow is in K20 squared times A to the T times V to the T. So again, I could just take it from here. That looks good, I think. I didn't take it from the other spot in the other column. Go on down, come on, down, 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 faster, faster. There we go. And again, the goal here, well, is to find these sums. Here we want I-23 through I-37. And here we want N23 through N122. We're supposed to see the same relationship here. In the case we're on as 20, this is bigger than this, and therefore also by what I showed you in the Mathematica, this is also bigger than this, and we are immunized. Okay, let me just double check that. Yeah, that looks good. In the case we're on as 15, we were not immunized. This is smaller than this. Same goes for this. This is smaller than this. Double check that. Yes, that looks good. This is smaller than this. So again, just emphasizing what we saw down here in this part. Okay, that's a lot of content as usual. I hope you got a lot out of it.